Good morning, everyone. So welcome to my YouTube channel, Math Satpuram. So today we are going to see a question. Let F G to G be homomorphism of G. Suppose F commutes with every inner automorphism of G. Then we are to show first K X belongs to G such that F square X is equal to Fx is a normal subgroup of G. Second one, G quotient K is abelian group. Okay, let's see how we will be proved. Okay. So first we are to show that K is equal to X belongs to G such that F square X is equal to Fx is a normal subgroup of G. Okay. So first of all, we have to show that K is 5, not equal to 5. It means K is non-empty. Now E belongs to G. So we are to show first thing, this one. Okay. So first we have to show that K is actually non-empty subset. How? K is non-empty set. So identity belongs to G. Okay. And identity satisfies this condition. And what is F square? E is equal to F. It is F E. Okay. But F is a automorphism. Sorry, F is homomorphism from G to G. Homomorphisms take identity to identity. So it is E. So this implies that F square E is equal to F E. So E belongs to K. So this implies K is non-empty. Okay. Now, second one, let X, Y belongs to K. Then F square X, Y inverse. What is this? This is nothing but F, X, Y inverse. Okay. So this is F, X. By property of homomorphism, we have this one. So F, Fx, and F take inverse of F image. So this is, we have this one. So this is this. Okay. Now, again, using property of homomorphism, we have this one. And we have this one. Okay. Again, the image of the inverse, the image inverse, okay, under the homomorphism. So I can write this part F square X, and this part will be F, Y whole inverse. Okay. Okay. But this is what? F square is Fx because X belongs to K. Now what is this? This is again F square Y. So you can again write it because Y belongs to K. So this is Fy. Okay. Again, property of homomorphism, we can write it Fx F Y inverse. By property of homomorphism, we can write like that. So what we got, F square X Y inverse is this. So this implies X Y inverse belongs to K. Okay. So we start with K, these two elements X Y belongs to K, and we prove that X Y inverse is also belonging to K. So K is not equal to 5 and X Y belongs to K implies X Y inverse belongs to K. So this implies K is subgroup of G. Now we will show that K is normal subgroup. Let G belongs to G and X belongs to K. Then what is this? We need to show that G inverse X G, okay, belongs to K. So what we will do, we will take F here, F square. What is this? This is nothing but F G inverse X G. Okay. So what is this? What is this? This we can write F G inverse F X. Okay. And we can write it F G. Okay. So what is this? This is nothing but F. And what is this? This is F G inverse F X F G. This is F. What is this? This is nothing but F. This is nothing but F. This is behaving like this is inner automorphism F G, and this is X. Okay, but F commutes with inner automorphism. So this is, I can write F G F. Okay, X. Okay. Sorry, this is Fx. This is Fx. So this is Fx. Okay, but F commutes with inner automorphism, so Fg will come out and it will be Fx. Okay. Because F commute inner automorphism. So what is this? This is Fg, because Fg is inner automorphism, and this is F square X. F square F is nothing but F. Okay. Again, F commutes with. So you open this one. What is this? Again, by definition of inner automorphism, we have this one, Fx and Fg. Okay. Now what is this? This is nothing but Fg inverse Fx Fg. So what is this by property of homomorphism? So what we got? We got F square G inverse Xg is equal to F G inverse Xg. So this implies G inverse X G belongs to K. For G belongs to G and X belongs to K implies G inverse X G belongs to K. So this implies, okay. So now K is subgroup of G and G belongs to G, X belongs to K implies G inverse X G belongs to K. So this implies K is normal subgroup of G. Okay, so it is proved. First part is proved. Okay. Now move to second one. Now second part, G quotient K is abelian. We need to show. So G upon K is abelian. If and only X, Kx, Ky is equal to Ky, Kx for all X, Y belongs to G. And when this will happen, Kxy is equal to Kyx for all X, Y belongs to G. Okay. And when will this will happen? If and only if this will happen one minute. This will happen if and only Yx inverse Xy belongs to K. It means what? If and only X inverse Y inverse Xy belongs to K for all Xy belongs to G. For all Xy belongs to G. Now we need to check this. So G upon K is abelian. If and only we need to check this one, whether Xy belongs to G, this happens or not. So let's check. Now let Xy belongs to G. Then what is F square X inverse Y inverse Xy? What is this? What is this? This is F. Okay. This is F. Or you can check this one also if you want. No problem. You can check this one also if you want. Sorry, you can write here this one. So this is equal to this one. So this will come here. This will be x, y, y, x inverse. It will be x, y, x inverse, y inverse. Okay. So this is equal to for x, y belongs to D. We need to check this one. X inverse, y inverse. Okay. So what we can write this? So what we can write this? We can write f x, y, x inverse, f, y. Okay. We can write like this. Okay. So what is this? What is actually this? This is f, f, x inverse, y this is. Okay. And this is y of y. Now f commutes with inner automorphism. So f commutes with inner automorphism means what? I can write this as a f x inverse f y. Okay. Okay. I can write like that. Okay. So what is this now? So because f commutes with inner automorphism, so I can write like that. So open this now. This is nothing but f x f y x inverse f y. Okay. Okay. So what is this now? So here it is nothing but actually I'm making a mistake. It is y inverse here. This is y inverse. This is y inverse. This is y inverse. So y inverse can be written as fy inverse. We know fy inverse can be written like this. Okay. So now what is this? F. This is x. This is f y inverse inner automorphism. Okay. And what is this? This is x. Okay. Okay. Now use the definition f is homomorphism. So I can write like that f x f. Okay. So this is inverse here. Okay. This is x inverse. Okay. This is x inverse. So f y inverse x inverse. Okay. Okay. But f commutes with inner automorphism. If it commutes with inner automorphism, I can write like that f y inverse f x inverse. Okay. Now this can be written as how f y inverse. What is this? f x का inverse. Okay. Now what is this? How we can write this? What is this? This is applying this. Applying inner automorphism here. So what you will get, this is Fy, okay, Fx का inverse, okay, and what is this Fy inverse, okay. So you do not take it outside, you can take still it inside, no problem, okay. You can take inside it, no problem, because it commutes. If it commutes, I can write like that, okay. Now, do not take it outside, you can keep inside as well, no problem. This is F inverse. This is F inverse. Now, what is this? This is Fx, Fy, Fx inverse, and we can write it Fy inverse. By property of homomorphism, what we have? X, Y, X inverse, Y inverse. So what we have? F square X, Y, X inverse, Y inverse is equal to F, X, Y, X inverse, Y inverse. Okay. So this implies X, Y, X inverse, Y inverse belongs to K. So this implies X, Y, X inverse, Y inverse belongs to K for all X, Y belongs to G. Let's see it equation number 2. And we are saying equation first, this equation is. Okay. So from 1 and 2, what we have? Because this holds for every X, Y belongs to G. Okay. But from 1 and 2, what we have? This holds. Now G upon K becomes abelian. From 1 and 2, we have G quotient K is abelian group. So it is true. So today's lecture up to this, if you have any problem related to this, you can comment on my YouTube channel. Like, share, comment and subscribe my YouTube channel. Thank you very much for today's lecture. Thank you very much.